Hey, so this is Joseph, and this is the third and final part of the fourth chapter of Stewart's Calculus. And we're going to be talking about U substitutions. And so U substitutions, they're basically in the same way that the chain rule applies to differentiation and makes a lot of differentiation easier. The U substitutions, or the substitution rule, does the same thing for integrals. It's a method of solving integrals by sort of substituting a variable for a part of the function that's being integrated. All right, so let me just remind you what the chain rule is, because the substitution rule is pretty similar. So the chain rule, if we want to find the derivative of some function y with respect to x, and we can't do that directly, we would need to make a substitution. And you sub in some part of the function, or the variable u for some part of the function, and you can get dy with respect to u, so the derivative of y with respect to u, times the derivative of u with respect to x. And these cancel, and that works. So that's the chain rule. Now, the substitution rule, on the other hand, does the same thing for integrals, and we also use a parameter that we're going to call u. That's why we call it u substitution. So let's define variable u as some function g of x. And we talked about differentials earlier on in the course, so du will be equal to g prime of x dx, and if you remember, that is because the derivative of u with respect to x would be g prime of x. But we're writing it out like this because you need this differential in the integral if we're going to be integrating something with respect to x, which is what we're going to be doing. This is going to end up being inside of an integral. And so then given this, we can say that the integral of some function with respect to this new parameter u, with respect to u, will be equal to that same function of g of x, remember, because those we're just substituting them, times g prime of x dx, because remember, that is equal to du. So these two expressions are equal, and these two expressions are equal. Now, you may be asking, based on the way that this is phrased, it seems like, oh, we'll come across a bunch of functions with the u inside, and then we're going to have to take them out and solve them like this. No, generally it's the other way around. You'll encounter a problem where everything's in terms of x or some other variable, and you'll have to find the g, and then you'll also have to, and the important thing about the u substitutions, and this is why it doesn't work for solving all integrals, is you'll also have to find the derivative of g somewhere else in the function in order to properly make the substitution. And I'm going to show you basically what I mean by that right now. We're going to do a practice problem from your book, number 25 from page 336. And what this problem gives us is it gives us an integral, the square root of cotangent x times secant squared x dx. So, we know that in order to use the u substitution, we need to find some thing in the function that's being integrated where we'll also be able to find its derivative elsewhere. And so in this case, this kind of makes it pretty obvious, pretty nice. Cotangent, we know that the derivative of cotangent is cosecant squared. So we're good. We know that we're able to make a u substitution. So what I'll do out here is I'll define u, which is g of x. I'll define g of x as cotangent x. And then I'll define g prime of x as cosecant squared x, because that is what g prime, and so that means that du, which is g prime of x dx, is going to be equal to cosecant squared x dx. And now, because this expression, based on this talk right here, that expression is equal to root g of x, g prime of x dx, based on the substitution rule, that is also that we can write that actually as root u du. And now we know how to integrate this with respect to u. Because that's a function that we know how to integrate. So let's integrate it. We can rewrite that as u to the 1/2 du, just to make it visually a little bit easier. So remember, we have to find the antiderivative of this. And because it's indefinite, the antiderivative has a plus c on it, and we can just write the plus c. Basically, we're just finding the antiderivative in this case, since it's an indefinite integral. So we add 1, so that'll make it 3/2, and then we divide it. So we have 2/3 out here, u 3/2 plus c. Now, when we're finding the answer, this is just an arbitrary kind of variable that we assigned in here. So this isn't the full answer. That u means something else. Specifically, if we go back up here, that u is g of x, and g of x is cotangent x. So we can substitute that in. 2/3 cotangent to the 3/2 x plus c. And that is that integral. Now you might ask, well, what about this plus c? This plus c we got in terms of u. Why do we have the same plus c here? Well, actually we don't. Those are different constants, but it doesn't really matter because that constant will change, but it will remain a constant, and it will remain a constant that we don't know. So you can just carry down that plus c, even though technically, implicitly, they mean different things. So that's how we solve an indefinite integral using the substitution rule. But let's change it up a little bit from what the book says. Let's say that this was a definite integral, namely the definite integral from pi over 4 to pi over 2 root cotangent x cosecant squared x dx. Well, let's just try to solve this in the same way as the previous method, and the previous problem, and it will be mostly the same. So we'll get out here u is equal to cotangent x, du is equal to cosecant squared x dx, and we can write this out then. I'm going to skip a couple of steps because they're going to be exactly the same, but we'll be able to write this as root u du. But now what about the limits? Do the limits change because based on the fact that our variables change? Yes. And how do we figure out how they change? Well, actually pretty easily, because we have this function out here, that equality right there. So remember implicitly that u is a function. It's a function g of x cotangent x. So we want to figure out what these limits are up here in terms of u, so we can continue them down there on the definite integral. Well, all we have to do is plug in pi over 2 for g of x and see what u is at that point. So cotangent of pi over 2 is equal to 0. So that means that the u for that limit is going to be 0. So you can write a 0 up there. And then the cotangent of pi over 4, that is equal to 1. So that means that the u for the bottom limit, in terms of u, is going to be 1. So then let's solve for this. It's going to be the same thing. 2/3 u to the 3/2 from 1 to 0. Now, what we could do the same thing that we did previously. We substitute back in cotangent for u, and then we change these limits back to as they are right here. But this is the nice thing about different definite integrals and changing the limits early, is we don't have to do that. We'd get the same thing through that method as we would just putting these limits in for u right here. And honestly, putting limits in for u right here using this function, this antiderivative, and subtracting the antiderivative at this value and that value is actually a lot easier than should we go back to the original function. So That's a nice trick for speed when you're on the AP and just like ease of calculation. So we will make that equal to 0 minus, and then plug in 1 for u, so that would just be 2/3, and then that'll just end up being negative 2/3. Alright, so let's do a practice problem in the book to kind of show how this u substitution business works. So we're going to do number 25 from page 336 in your book, and what it gives us this integral, the integral of root cotangent x cosecant squared x dx. And if we were going to go solve this in some of the methods that we've learned earlier, we wouldn't have a way of doing so. We'd need to use u substitutions. And we know that u substitution is the method, because that we will learn other methods later on in the course. However, right now we know that u substitution can work because we see an expression cotangent x, and its derivative is negative cosecant squared x, and don't really pay attention to the negative right now. We can sort that out later. But the bulk of the expression is to be found in the rest of the integral. So that means we can use the u substitution method. So we'll have a variable u, define that as a function g of x, and because cotangent is the one that has its derivative later in the expression, we will make g of x cotangent x, and then du g prime of x dx, and the derivative of g is going to be negative cosecant squared x, and that dx carries over. So that means that we can write this expression, that expression actually is root g of x times, and now wait, this expression right there isn't exactly g prime of x dx, because there's this negative, and there's no negative here. But because the negative is just a constant, we can add the negative in. Actually, not add it in, divide it in. But since it's a negative, it'll still show up as negative. So we can throw a little negative off to the front here, and then it's g prime of x dx. And so because of the substitution rule, and we'll just carry this negative straight through, we can also write that out as root u du with the negative. And we know how to solve this integral. This is an kind of integral we've solved before. We've solved square root functions as integrals. And so that means we can write this out as, well, to simplify, 1/2 du, and then we add 1 to the exponent, divide it into the coefficient. So that is u to the 3/2 times 2/3. Don't forget the negative. And because this is an indefinite integral, we don't have to subtract the antiderivative at one point, and another point we can just add the plus c in there. And so this is not our final result because the u is just kind of an arbitrary function we've defined. We need to put it back in terms of x, and luckily we have an expression for that right there, u equals cotangent of x, so we just substitute that in. We get negative 2/3 cotangent to the 3/2 x plus c. And that is that integral. And you might be asking, why do I write the plus c down here and up here when this one is attached to a function in terms of u and this c is attached to a function in terms of x? Aren't they different c's? The answer is yeah, they are different c's. However, because we won't know what that c is equal to either way without having some prior constraints, we can just carry it down and write it because it's still an arbitrary shift, or it represents any number of different kinds of shifts that you could apply to either expression, although they're both going to be different if we had some constraints. So that's how you solve that. And now let's change this problem a little bit, just for the sake of kind of conceptualizing things and also doing new kinds of problems. Let's say that this wasn't an indefinite integral, it was a definite integral with some limits on it. Specifically, let's say those limits were pi over 4 down here, pi over 2 up here, and it was the same function inside, so it was root cotangent x times cosecant x dx. Well, let's just begin trying to solve this in the same way we solved the previous problem. And we'll actually use the same u substitution. So let's just write it out here to remind ourselves. U is cotangent x, du is negative cosecant squared x dx. So we can write this out as negative root u du. However, what are the limits here? Are the limits the same as the limits up here? No, because they're in terms of different variables. But how do we then determine what these limits are? Well, we have these substitution expressions up here that'll let us do that. So we need to find out what the value of u is when x is pi over 2. And that's super easy. When x is pi over 2, we've got cotangent pi over 2, and that's what u is going to be equal to. And cotangent of pi over 2 is 0, so we can put 0 up there. And then what is u going to be when x is pi over 4? Well, u is going to be equal to cotangent of pi over 4, and cotangent of pi over 4 is 1, so we can put a 1 down here in the bottom. Now, technically there are two ways we can go right here. We could just solve this indefinite integral straight away and keep it in terms of u and plug in these limits for the antiderivative in terms of u. Or we could solve the antiderivative in terms of u, put it back in terms of x, put the limits back in terms of x, and then go from there. The second way that I just described would be long. It's kind of difficult to deal with trig functions, like substituting values in, whereas this would be one variable to a power, which isn't too complicated most of the times to do a substitution for, and it works. Well, you'd get the same answer either way. So with indefinite integrals like this, if you change the limit values at this point, you can keep it in terms of u the entire time, and that's what we're going to do. So integrate that. It's going to be the same as last time, u to the 3/2 plus c. Or actually, sorry, no plus c, because this is a definite integral. We're going to subtract this antiderivative at one point and another point, so between 0 and 1. And we get 0, minus, and a minus, that's a plus, plus 2/3, and then, yeah, and then we come out, and we will get 2/3, and that is the value of that indefinite integral. And so there you go, that's the u substitution method. That's how it works for definite and indefinite integrals, and stay tuned for the next chapter where we're going to be talking about more applications of integrals for area and volume. It's super interesting, so be stoked for that. Bye.